Next up, we have Dr. Liken Zhang, who's a data scientist at Methodist Hospital, who will be speaking on using interpretability to help improve model performance in human diagnosis.
Hello, can you hear me? Is this good? Okay, thank you. Good afternoon, everyone. My name is Liken Zhang. Today, my talk is about using interpretation techniques to help improve the model performance and human diagnosis. And so here's the overview for this talk. And this study is about melanoma classifications. A little bit of background about melanoma. Melanoma is one of the most aggressive and serious type of skin cancer in the world, and it accounts for 75% of skin cancer deaths. Melanoma is coming from a normal cell called the melanocyte, which is in the epidermis. When this melanocyte become abnormal, and it probably will develop into a melanoma. For doctors or persons, there is a visual examination guideline called ABCDE. A stands for asymmetry, B stands for border, C stands for color, D stands for diameter, and E stands for evolving. So if you see some spot on your body which is not symmetric, and the body is irregular, and the color is not uniform, and the size is larger than a pencil eraser, and or maybe it starts to bleed or become bigger, then it's very suspicious. So maybe it's time to see a doctor and get tested. And as with other cancers, for melanoma, early detection is very important, because at the later stage of the melanoma, the cancer cell will be transferred to other organs of the human body, and it's very difficult to remove completely. So the goal is to achieve this early detection with the help of data science. So from the data science perspective, what we like to have is a standard pipeline that can go from the raw data and to the end for deployment. Today's talk is mainly focusing on the middle part. So we're trying to use the interpretation technique to help improve the model performance. Usually there is a trade-off between the model accuracy and the interpretability. So when we use some simpler model like a linear regression, it's easier to interpret, but the accuracy is very limited. When we use a complex model like neural network or deep neural network, the accuracy can reach very high, but it's kind of difficult to interpret. So people is struggling what's going on inside in the black box. So that's why many people have developed visualization techniques. I list a few here: class activation map, guided backpropagation, deconvolution, Gradicant. It's a gradient-based CAM, which is a tool we use here, and SHAP is a game theory-based method. So for tasks like melanoma classification, the model approach is like following. So we input the image of the skin into a convolutional layers, convolutional models, and combine with some metadata, and we can output a probability for the melanoma. Then we can use some visualization techniques. For example, Gradicant, it can generate this kind of heat map. The heat map highlights the regions where the model thinks it contributes most to the output of the prediction here. But there is not too much paper or research people talking about what can we do next. How can we use this kind of visualization knowledge here? So here we propose two new ideas. One is for the pre-processing step, like doing new data augmentation, and one is for the post-processing, so we can train a second model. But both we want to use the heat map generated from the Grad-CAM. So comparing Gradicant and SHAP. So like I mentioned, Gradicant can highlight the important regions in the image for the prediction. So this example here just showing when the class is cat, and the Gradicant can capture the region where the cat sits in the picture. And this indicates, where the part of the image contributes to the final prediction. And on the other hand, SHAP is kind of doing a similar thing, but it's game theory based. So it has a very solid theory foundation here. So for example, if for this image, the model can predict this image to be Darwincher with probability 0.95, and the SHAP can decompose this 0.95 into values, sharply values for each pixel on the image. So if you sum all the sharply value from this image, you will get 0.95. And here is the scale bar for red means positive contribution, and blue means negative contribution. But SHAP is very computationally expensive, so it takes a long time to generate something like a heat map. So for the next content, we will just use result with the Gradicant here. So here just showing some examples of the Grad-CAM on the melanoma dataset. And what's interesting here is actually we see the region captured by the Gradicant matches some of the ABCDE guideline here. So you can see it captured the difference between the colors and some irregular boundaries of this spot here. So the data we use is from ISIC 2019 and 2020 dataset. And the percentage for melanoma is about 9%. So it's imbalanced, but not that imbalanced. We put some weights in the loss function in the training here. And the metric we're looking at is the area under the ROC curve. We're trying to see how good the classifier performs. We're not dealing with some thresholding at this moment, because in order to have some confusion matrix, false positive, false negative, you should have a thresholding, 0.5 or 0.6, but we're not doing that at this moment. So the metric is AUC here, showing some example of the benign ones. Benign is 0 in the label in the data, and the malignant is a melanoma, so the label is 1. So the first idea is about the preprocessing improvement. So for the first step, we can train a decent model here using our regular training step, regular data augmentation. Then we can output a probability for melanoma, and also we can apply the Gradicant to generate heat map for each samples. The new idea here is we can use this heat map to generate some mask and cut out regions from the samples. Then we can mix with regions from samples from the other class. So the demo here is showing that this is a malignant sample, and we generate a Gradicant heat map, and it's highlighting this region here. I think this is why the prediction is low here. And we can cut out this region and mix with some region from the benign samples. But not just any regions in the benign samples. We also use this Gradicant to generate heat map, so we can take some useful regions from the benign sample and mix them here. So we call this customized cut mix data augmentation. So we use this to retrain the model, or we can train on top of the original baseline model here. But here we want to see how good this idea is, so we retrain the model using this new data augmentation. This cut mix name is coming from this paper, but the original code does not work very well with this data set, because the original one is just doing a randomly cut and mix, but it's not making sense here, just doing a randomly cut. So here, just showing some results here. The model we use is the EfficientNet B0. We use this one for the CNN part and combined with some metadata. And for the training data, we see the improvement in the 5-fold cross-validation AUC. And also we do some data validation on some unseen data here. What's interesting is this unseen data, actually we did not pick them by ourselves. It's by someone else. So it's kind of trying to mimic the real life, because in cases in the real life, you probably don't have some validation data set that have the same distribution as the training data set. So that's why you see the difference between the unseen data and the training data. But we see the improvement of this method on unseen data as well. And trying to validate this method, we apply the Gradicant again to the model that we retrained. And you can see it can capture the region that makes more sense than the baseline. And the accuracy, the prediction is more accurate. And the region is making more sense around this melanoma region here. And for second idea is about post-processing improvement. This is inspired by the negative feedback loop in the control series. So we can train a model, very decent one, but no matter how good the model is, you always have some false positive and false negative here. So we are trying to train a second model that targets the probability residual here. So you have some target labels, and this is a prediction from the model 1. Then we can calculate the residual, it's target minus prediction. And the idea is we want to train a second model trying to estimate this residual. So the final prediction will be the sum of output from model 1 and model 2 here. One of the inspiration is for coming from example like this. They are both malignant, but from model 1, the prediction for this one is more confident, and this one is totally not confident. But from the heat map generated by Grad-CAM, it both capture the important region here. So the idea is if we can incorporate this heat map combined with the input and also the prediction from model 1, we want the model 2 to estimate the probability residual. Trying to so we can use this one to improve the results from model 1. And same thing here, we see some improvement in the training data set, but on the data validation, we see not big difference here. Again, I think the data validation data don't have the same kind of distribution as the training data here. And I believe there is room to improve for the second idea. So at last, for some future work, so we think the two ideas can be combined and also can be combined with other methods. And also, since we only use B0 here, we can try some better model like B3 or up to B7. So hoping them can capture better results in the heat map. And also, if this is going well, we can make this process more automatic and let the model keep training and by itself. And from the disease itself, we can consider some other perspectives. For example, by looking at the immune profiling using some new technology called CyTOF and IMC on the biopsy samples. And here the reference. Thank you.
Thank you. That was really interesting. One quick question,
Yes.
and a reminder to put questions in the chat if you have them. But so we have these criteria that physicians use when they're looking at melanomas, and can you tell if the models are looking at the same set of criteria, or are they looking at something totally different?
Yeah, I think the model can capture some similar features that the doctor are looking at. And also another purpose we want to use this visualization to see if the model can give some new perspective that it's not in the presence of the doctor's examination.
Yeah, absolutely. Thank you. Well, we better move on if there are no other questions.